Unit 3. The Heart 9. Cardiac muscle, the heart as a pump and function of the heart valves 10. Rhythmical excitation of the heart 11. The normal electrocardiogram 12. Electrocardiographic interpretation of cardiac muscle and coronary blood flow abnormalities, vectorial analysis 13. Cardiac arrhythmias and their electrocardiographic interpretation. Chapter 9. Cardiac muscle, the heart as a pump and function of the heart valves. With this chapter we begin discussion of the heart and circulatory system. The heart, shown in Figure 9.1, is actually two separate pumps, a right heart that pumps blood through the lungs, and a left heart that pumps blood through the peripheral organs. In turn, each of these hearts is a pulsatile two-chamber pump composed of an atrium and a ventricle. Each atrium is a weak primer pump for the ventricle, helping to move blood into the ventricle. The ventricles then supply the main pumping force that propels the blood either, 1, through the pulmonary circulation by the right ventricle or, 2, through the peripheral circulation by the left ventricle. Special mechanisms in the heart cause a continuing succession of heart contractions called cardiac rhythmicity, transmitting action potentials throughout the cardiac muscle to cause the heart's rhythmical beat. This rhythmical control system is explained in Chapter 10. In this chapter, we explain how the heart operates as a pump, beginning with the special features of cardiac muscle itself. Physiology of cardiac muscle. The heart is composed of three major types of cardiac muscle: atrial muscle, ventricular muscle, and specialized excitatory and conductive muscle fibers. The atrial and ventricular types of muscle contract in much the same way as skeletal muscle, except that the duration of contraction is much longer. The specialized excitatory and conductive fibers, however, contract only feebly because they contain few contractile fibrils. Instead, they exhibit either automatic rhythmical electrical discharge in the form of action potentials or conduction of the action potentials through the heart, providing an excitatory system that controls the rhythmical beating of the heart. Physiologic anatomy of cardiac muscle. Figure 9.2 shows the histology of cardiac muscle, demonstrating cardiac muscle fibers arranged in a latticework, with the fibers dividing, recombining, and then spreading. Again, one also notes immediately from this figure that cardiac muscle is striated in the same manner as in skeletal muscle. Further, cardiac muscle has typical myofibrils that contain actin and myosin filaments almost identical to those found in skeletal muscle. These filaments lie side by side and slide along one another during contraction in the same manner as occurs in skeletal muscle, see Chapter 6. But in other ways, cardiac muscle is quite different from skeletal muscle, as we shall see. Cardiac muscle as a syncytium. The dark areas crossing the cardiac muscle fibers in Figure 9.2 are called intercalated discs. They are actually cell membranes that separate individual cardiac muscle cells from one another. That is, cardiac muscle fibers are made up of many individual cells connected in series and in parallel with one another. At each intercalated disc the cell membranes fuse with one another in such a way that they form permeable communicating junctions, gap junctions, that allow rapid diffusion of ions. Therefore, from a functional point of view, ions move with ease in the intracellular fluid along the longitudinal axes of the cardiac muscle fibers so that action potentials travel easily from one cardiac muscle cell to the next, past the intercalated discs. Thus, cardiac muscle is a syncytium of many heart muscle cells in which the cardiac cells are so interconnected that when one of these cells becomes excited, the action potential spreads to all of them, from cell to cell throughout the latticework interconnections. The heart actually is composed of two syncytiums, the atrial syncytium, which constitutes the walls of the two atria, and the ventricular syncytium, which constitutes the walls of the two ventricles. The atria are separated from the ventricles by fibrous tissue that surrounds the atrioventricular, AV, valvular openings between the atria and ventricles. Normally, potentials are not conducted from the atrial syncytium into the ventricular syncytium directly through this fibrous tissue. Instead, they are conducted only by way of a specialized conductive system called the AV bundle, a bundle of conductive fibers several millimeters in diameter that is discussed in detail in Chapter 10. This division of the muscle of the heart into two functional syncytiums allows the atria to contract a short time ahead of ventricular contraction, which is important for effectiveness of heart pumping. Action potentials in cardiac muscle. The action potential recorded in a ventricular muscle fiber, shown in Figure 9.3, averages about 105 millivolts, which means that the intracellular potential rises from a very negative value, about -85 millivolts, between beats to a slightly positive value, about +20 millivolts, during each beat. After the initial spike, the membrane remains depolarized for about 0.2 seconds, exhibiting a plateau as shown in the figure, followed at the end of the plateau by abrupt repolarization. The presence of this plateau in the action potential causes ventricular contraction to last as much as 15 times as long in cardiac muscle as in skeletal muscle. What causes the long action potential and the plateau? At this point, we address the questions: why is the action potential of cardiac muscle so long, and why does it have a plateau, whereas that of skeletal muscle does not? The basic biophysical answers to these questions were presented in Chapter 5, but they merit summarizing here as well. At least two major differences between the membrane properties of cardiac and skeletal muscle account for the prolonged action potential and the plateau in cardiac muscle. First, the action potential of skeletal muscle is caused almost entirely by sudden opening of large numbers of so-called fast sodium channels that allow tremendous numbers of sodium ions to enter the skeletal muscle fiber from the extracellular fluid. These channels are called fast channels because they remain open for only a few thousandths of a second and then abruptly close. At the end of this closure, repolarization occurs, and the action potential is over within another thousandth of a second or so. In cardiac muscle, the action potential is caused by opening of two types of channels: 1, the same fast sodium channels as those in skeletal muscle, and 2, another entirely different population of slow calcium channels, which are also called calcium-sodium channels. This second population of channels differs from the fast sodium channels in that they are slower to open and, even more important, remain open for several tenths of a second. During this time, a large quantity of both calcium and sodium ions flows through these channels to the interior of the cardiac muscle fiber, and this maintains a prolonged period of depolarization, causing the plateau in the action potential. Further, the calcium ions that enter during this plateau phase activate the muscle contractile process, while the calcium ions that cause skeletal muscle contraction are derived from the intracellular sarcoplasmic reticulum. The second major functional difference between cardiac muscle and skeletal muscle that helps account for both the prolonged action potential and its plateau is this: immediately after the onset of the action potential, the permeability of the cardiac muscle membrane for potassium ions decreases about fivefold, an effect that does not occur in skeletal muscle. This decreased potassium permeability may result from the excess calcium influx through the calcium channels just noted. Regardless of the cause, the decreased potassium permeability greatly decreases the outflux of positively charged potassium ions during the action potential plateau and thereby prevents early return of the action potential voltage to its resting level. When the slow calcium-sodium channels do close at the end of 0.2 to 0.3 seconds and the influx of calcium and sodium ions ceases, the membrane permeability for potassium ions also increases rapidly. This rapid loss of potassium from the fiber immediately returns the membrane potential to its resting level, thus ending the action potential. Velocity of signal conduction in cardiac muscle. The velocity of conduction of the excitatory action potential signal along both atrial and ventricular muscle fibers is about 0.3 to 0.5 meters per second, or about 1/250th the velocity in very large nerve fibers and about 1/10th the velocity in skeletal muscle fibers. The velocity of conduction in the specialized heart conductive system, in the Purkinje fibers, is as great as 4 meters per second in most parts of the system, which allows reasonably rapid conduction of the excitatory signal to the different parts of the heart, as explained in Chapter 10. Refractory period of cardiac muscle. Cardiac muscle, like all excitable tissue, is refractory to restimulation during the action potential. Therefore, the refractory period of the heart is the interval of time, as shown to the left in Figure 9.4, during which a normal cardiac impulse cannot re-excite an already excited area of cardiac muscle. The normal refractory period of the ventricle is 0.25 to 0.30 second, which is about the duration of the prolonged plateau action potential. There is an additional relative refractory period of about 0.05 second during which the muscle is more difficult than normal to excite but nevertheless can be excited by a very strong excitatory signal, as demonstrated by the early premature contraction in the second example of Figure 9.4. The refractory period of atrial muscle is much shorter than that for the ventricles, about 0.15 second for the atria compared with 0.25 to 0.30 second for the ventricles. Excitation contraction coupling. Function of calcium ions and the transverse tubules. The term excitation contraction coupling refers to the mechanism by which the action potential causes the myofibrils of muscle to contract. This was discussed for skeletal muscle in Chapter 7. Once again, there are differences in this mechanism in cardiac muscle that have important effects on the characteristics of heart muscle contraction. As is true for skeletal muscle, when an action potential passes over the cardiac muscle membrane, the action potential spreads to the interior of the cardiac muscle fiber along the membranes of the transverse T tubules. The T-tubule action potentials in turn act on the membranes of the longitudinal sarcoplasmic tubules to cause release of calcium ions into the muscle sarcoplasm from the sarcoplasmic reticulum. In another few thousandths of a second, these calcium ions diffuse into the myofibrils and catalyze the chemical reactions that promote sliding of the actin and myosin filaments along one another. This produces the muscle contraction. Thus far, this mechanism of excitation contraction coupling is the same as that for skeletal muscle, but there is a second effect that is quite different. In addition to the calcium ions that are released into the sarcoplasm from the systole of the sarcoplasmic reticulum, calcium ions also diffuse into the sarcoplasm from the T-tubules themselves at the time of the action potential, which opens voltage-dependent calcium channels in the membrane of the T-tubule. Figure 9.5. Calcium entering the cell then activates calcium release channels, also called ryanodine receptor channels, in the sarcoplasmic reticulum membrane, triggering the release of calcium into the sarcoplasm. Calcium ions in the sarcoplasm then interact with troponin to initiate cross-bridge formation and contraction by the same basic mechanism as described for skeletal muscle in Chapter 6. Without the calcium from the T-tubules, the strength of cardiac muscle contraction would be reduced considerably because the sarcoplasmic reticulum of cardiac muscle is less well developed than that of skeletal muscle and does not store enough calcium to provide full contraction. The T-tubules of cardiac muscle, however, have a diameter 5 times as great as that of the skeletal muscle tubules, which means a volume 25 times as great. Also, inside the T-tubules is a large quantity of mucopolysaccharides that are electronegatively charged and bind an abundant store of calcium ions, keeping these always available for diffusion to the interior of the cardiac muscle fiber when a T-tubule action potential appears. The strength of contraction of cardiac muscle depends to a great extent on the concentration of calcium ions in the extracellular fluids. In fact, a heart placed in a calcium-free solution will quickly stop beating. The reason for this is that the openings of the T-tubules pass directly through the cardiac muscle cell membrane into the extracellular spaces surrounding the cells, allowing the same extracellular fluid that is in the cardiac muscle interstitium to percolate through the T-tubules as well. Consequently, the quantity of calcium ions in the T-tubule system, that is, the availability of calcium ions to cause cardiac muscle contraction, depends to a great extent on the extracellular fluid calcium ion concentration. In contrast, the strength of skeletal muscle contraction is hardly affected by moderate changes in extracellular fluid calcium concentration because skeletal muscle contraction is caused almost entirely by calcium ions released from the sarcoplasmic reticulum inside there. Skeletal muscle fiber. At the end of the plateau of the cardiac action potential, the influx of calcium ions to the interior of the muscle fiber is suddenly cut off, and the calcium ions in the sarcoplasm are rapidly pumped back out of the muscle fibers into both the sarcoplasmic reticulum and the T-tubule extracellular fluid space. Transport of calcium back into the sarcoplasmic reticulum is achieved with the help of a calcium ATPase pump. See Figure 9.5. Calcium ions are also removed from the cell by a sodium-calcium exchanger. The sodium that enters the cell during this exchange is then transported out of the cell by the sodium-potassium ATPase pump. As a result, the contraction ceases until a new action potential comes along. Duration of contraction. Cardiac muscle begins to contract a few milliseconds after the action potential begins and continues to contract until a few milliseconds after the action potential ends. Therefore, the duration of contraction of cardiac muscle is mainly a function of the duration of the action potential, including their plateau, about 0.2 second in atrial muscle and 0.3 second in ventricular muscle. Cardiac cycle. The cardiac events that occur from the beginning of one heartbeat to the beginning of the next are called the cardiac cycle. Each cycle is initiated by spontaneous generation of an action potential in the sinus node, as explained in Chapter 10. This node is located in the superior lateral wall of the right atrium near the opening of the superior vena cava, and the action potential travels from here rapidly through both atria and then through the AV bundle into the ventricles. Because of this special arrangement of the conducting system from the atria into the ventricles, there is a delay of more than 0.1 second during passage of the cardiac impulse from the atria into the ventricles. This allows the atria to contract ahead of ventricular contraction, thereby pumping blood into the ventricles before the strong ventricular contraction begins. Thus, the atria act as primer pumps for the ventricles, and the ventricles in turn provide the major source of power for moving blood through the body's vascular system. Diastole and systole. The cardiac cycle consists of a period of relaxation called diastole, during which the heart fills with blood, followed by a period of contraction called systole. The total duration of the cardiac cycle, including systole and diastole, is the reciprocal of the heart rate. For example, if heart rate is 72 beats per minute, the duration of the cardiac cycle is 172 beats per minute, about 0.0139 minutes per beat, or 0.833 second per beat. Figure 9.6 shows the different events during the cardiac cycle for the left side of the heart. The top three curves show the pressure changes in the aorta, left ventricle, and left atrium, respectively. The fourth curve depicts the changes in left ventricular volume, the fifth the electrocardiogram, and the sixth the phonocardiogram, which is a recording of the sounds produced by the heart, mainly by the heart valves, as it pumps. It is especially important that the reader study in detail this figure and understand the causes of all the events shown. Effect of heart rate on duration of cardiac cycle. When heart rate increases, the duration of each cardiac cycle decreases, including the contraction and relaxation phases. the duration of the action potential and the period of contraction, systole, also decrease, but not by as great a percentage as does the relaxation phase, diastole. At a normal heart rate of 72 beats per minute, systole comprises about 0.4 of the entire cardiac cycle. At 3 times the normal heart rate, systole is about 0.65 of the entire cardiac cycle. This means that the heart beating at a very fast rate does not remain relaxed long enough to allow complete filling of the cardiac chambers before the next contraction. Relationship of the electrocardiogram to the cardiac cycle. The electrocardiogram in Figure 9.6 shows the P, Q, R, S, and T waves, which are discussed in chapters 11, 12, and 13. They are electrical voltages generated by the heart and recorded by the electrocardiograph from the surface of the body. The P wave is caused by spread of depolarization through the atria, and this is followed by atrial contraction, which causes a slight rise in the atrial pressure curve immediately after the electrocardiographic P wave. About 0.16 second after the onset of the P wave, the QRS waves appear as a result of electrical depolarization of the ventricles, which initiates contraction of the ventricles and causes the ventricular pressure to begin rising, as also shown in the figure. Therefore, the QRS complex begins slightly before the onset of ventricular systole. Finally, one observes the ventricular T wave in their electrocardiogram. This represents the stage of repolarization of the ventricles when the ventricular muscle fibers begin to relax. Therefore, the T wave occurs slightly before the end of ventricular contraction. Function of the atria. As primer pumps blood normally flows continually from the great veins into the atria, about 80% of the blood flows directly through the atria into the ventricles even before the atria contract. Then, atrial contraction usually causes an additional 20% filling of the ventricles. Therefore, the atria simply function as primer pumps that increase the ventricular pumping effectiveness as much as 20%. However, the heart can continue to operate under most conditions, even without this extra 20% effectiveness, because it normally has the capability of pumping 300 to 400% more blood than is required by the resting body. Therefore, when the atria fail to function, the difference is unlikely to be noticed unless a person exercises. Then acute signs of heart failure occasionally develop, especially shortness of breath. Pressure changes in the atria, A, C, and V waves. In the atrial pressure curve of Figure 9.6, 3 minor pressure elevations, called the A, C, and V atrial pressure waves, are noted. The A wave is caused by atrial contraction. Ordinarily, the right atrial pressure increases 4 to 6 mm Hg during atrial contraction, and the left atrial pressure increases about 7 to 8 mm Hg. The C wave occurs when the ventricles begin to contract. It is caused partly by slight backflow of blood into the atria at the onset of ventricular contraction, but mainly by bulging of the AV valves backward toward the atria because of increasing pressure in the ventricles. The V wave occurs toward the end of ventricular contraction. It results from slow flow of blood into the atria from the veins while the AV valves are closed during ventricular contraction. Then, when ventricular contraction is over, the AV valves open, allowing this stored atrial blood to flow rapidly into the ventricles and causing the V wave to disappear. Function of the ventricles as pumps. Filling of the ventricles during diastole. During ventricular systole, large amounts of blood accumulate in the right and left atria because of the closed AV valves. Therefore, as soon as systole is over and the ventricular pressures fall again to their low diastolic values, the moderately increased pressures that have developed in the atria during ventricular systole immediately push the AV valves open and allow blood to flow rapidly into the ventricles, as shown by the rise of the left ventricular volume curve in Figure 9.6. This is called the period of rapid filling of the ventricles. The period of rapid filling lasts for about the first third of diastole. During the middle third of diastole, only a small amount of blood normally flows into the ventricles. This is blood that continues to empty into the atria from the veins and passes through the atria directly into the ventricles. During the last third of diastole, the atria contract and give an additional thrust to the inflow of blood into the ventricles. This accounts for about 20% of the filling of the ventricles during each heart cycle. Emptying of the ventricles during systole period of isovolumic, isometric, contraction. Immediately after ventricular contraction begins, the ventricular pressure rises abruptly, as shown in Figure 9.6, causing the AV valves to close. Then an additional 0.02 to 0.03 second is required for the ventricle to build up sufficient pressure to push the semilunar, aortic and pulmonary valves open against the pressures in the aorta and pulmonary artery. Therefore, during this period, contraction is occurring in the ventricles, but there is no emptying. This is called the period of isovolumic or isometric contraction, meaning that tension is increasing in the muscle but little or no shortening of the muscle fibers is occurring. Period of ejection. When the left ventricular pressure rises slightly above 80 mm Hg, and the right ventricular pressure slightly above 8 mm Hg, the ventricular pressures push the semilunar valves open. Immediately, blood begins to pour out of the ventricles, with about 70% of the blood emptying occurring during the first third of the period of ejection and the remaining 30% emptying during the next two-thirds. Therefore, the first third is called the period of rapid ejection, and the last two-thirds, the period of slow ejection. Period of isovolumic, isometric, relaxation. At the end of systole, ventricular relaxation begins suddenly, allowing both the right and left intraventricular pressures to decrease rapidly. The elevated pressures in the distended large arteries that have just been filled with blood from the contracted ventricles immediately push blood back toward the ventricles, which snaps the aortic and pulmonary valves closed. For another 0.03 to 0.06 second, the ventricular muscle continues to relax, even though the ventricular volume does not change, giving rise to the period of isovolumic or isometric relaxation. During this period, the intraventricular pressures decrease rapidly back to their low diastolic levels. Then the AV valves open to begin a new cycle of ventricular pumping. End diastolic volume, and systolic volume, and stroke volume output. During diastole, normal filling of the ventricles increases the volume of each ventricle to about 110 to 120 milliliters. This volume is called the end diastolic volume. Then, as the ventricles empty during systole, the volume decreases about 70 milliliters, which is called the stroke volume output. The remaining volume in each ventricle, about 40 to 50 milliliters, is called the end systolic volume. The fraction of the end diastolic volume that is ejected is called the ejection fraction, usually equal to about 60%. When the heart contracts strongly, the end systolic volume can be decreased to as little as 10 to 20 milliliters. Conversely, when large amounts of blood flow into the ventricles during diastole, the ventricular end diastolic volumes can become as great as 150 to 180 milliliters in the healthy heart. By both increasing the end diastolic volume and decreasing the end systolic volume, the stroke volume output can be increased to more than double normal. Function of the valves. Atrioventricular valves. The AV valves, the tricuspid and mitral valves, prevent backflow of blood from the ventricles to the atria during systole, and the semilunar valves, the aortic and pulmonary artery valves, prevent backflow from the aorta and pulmonary arteries into the ventricles during diastole. These valves, shown in Figure 9.7 for the left ventricle, close and open passively. That is, they close when a backward pressure gradient pushes blood backward, and they open when a forward pressure gradient forces blood in the forward direction. For anatomical reasons, the thin, filmy AV valves require almost no backflow to cause closure, whereas the much heavier semilunar valves require rather rapid backflow for a few milliseconds. Function of the papillary muscles. Figure 9.7 also shows papillary muscles that attach to the veins of the AV valves by the chordae tendineae. The papillary muscles contract when the ventricular walls contract, but contrary to what might be expected, they do not help the valves to close. Instead, they pull the veins of the valves inward toward the ventricles to prevent their bulging too far backward toward the atria during ventricular contraction. If a chordae tendineae becomes ruptured or if one of the papillary muscles becomes paralyzed, the valve bulges far backward during ventricular contraction, sometimes so far that it leaks severely and results in severe or even lethal cardiac incapacity. Aortic and pulmonary artery valves. The aortic and pulmonary artery semilunar valves function quite differently from the AV valves. First, the high pressures in the arteries at the end of systole cause the semilunar valves to snap to the closed position, in contrast to the much softer closure of the AV valves. Second, because of smaller openings, the velocity of blood ejection through the aortic and pulmonary valves is far greater than that through the much larger AV valves. Also, because of the rapid closure and rapid ejection, the edges of the aortic and pulmonary valves are subjected to much greater mechanical abrasion than are the AV valves. Finally, the AV valves are supported by the chordae tendineae, which is not true for the semilunar valves. It is obvious from the anatomy of the aortic and pulmonary valves, as shown for the aortic valve at the bottom of figure 9.7. That they must be constructed with an especially strong yet very pliable fibrous tissue base to withstand the extra physical stresses. Aortic pressure curve. When the left ventricle contracts, the ventricular pressure increases rapidly until the aortic valve opens. Then, after the valve opens, the pressure in the ventricle rises much less rapidly, as shown in figure 9.6. Because blood immediately flows out of the ventricle into the aorta and then into the systemic distribution arteries. The entry of blood into the arteries causes the walls of these arteries to stretch and the pressure to increase to about 120 mm Hg. Next, at the end of systole, after the left ventricle stops ejecting blood and the aortic valve closes, the elastic walls of the arteries maintain a high pressure in the arteries, even during diastole. A so-called incisura occurs in the aortic pressure curve when the aortic valve closes. This is caused by a short period of backward flow of blood immediately before closure of the valve, followed by sudden cessation of the backflow. After the aortic valve has closed, the pressure in the aorta decreases slowly throughout diastole because the blood stored in the distended elastic arteries flows continually through the peripheral vessels back to the veins. Before the ventricle contracts again, the aortic pressure usually has fallen to about 80 mm Hg, diastolic pressure, which is 2/3 the maximal pressure of 120 mm Hg, systolic pressure, that occurs in the aorta during ventricular contraction. The pressure curves in the right ventricle and pulmonary artery are similar to those in the aorta, except that the pressures are only about 1/6 as great, as discussed in Chapter 14. Relationship of the heart sounds to heart pumping. When listening to the heart with a stethoscope, one does not hear the opening of the valves because this is a relatively slow process that normally makes no noise. However, when the valves close, the veins of the valves and the surrounding fluids vibrate under the influence of sudden pressure changes, giving off sound that travels in all directions through the chest. When the ventricles contract, one first hears a sound caused by closure of the AV valves. The vibration is low in pitch and relatively long-lasting and is known as the first heart sound. When the aortic and pulmonary valves close at the end of systole, one hears a rapid snap because these valves close rapidly, and the surroundings vibrate for a short period. This sound is called the second heart sound. The precise causes of the heart sounds are discussed more fully in Chapter 23, in relation to listening to the sounds with the stethoscope. Work output of the heart. The stroke work output of the heart is the amount of energy that the heart converts to work during each heartbeat while pumping blood into the arteries. Minute work output is the total amount of energy converted to work in 1 minute. This is equal to the stroke work output times the heart rate per minute. Work output of the heart is in two forms. First, by far the major proportion is used to move the blood from the low-pressure veins to the high-pressure arteries. This is called volume pressure work or external work. Second, a minor proportion of the energy is used to accelerate the blood to its velocity of ejection through the aortic and pulmonary valves. This is the kinetic energy of blood flow component of the work output. Right ventricular external work output is normally about 1/6 the work output of the left ventricle because of the six-fold difference in systolic pressures that the two ventricles pump. The additional work output of each ventricle required to create kinetic energy of blood flow is proportional to the mass of blood ejected times the square of velocity of ejection. Ordinarily, the work output of the left ventricle required to create kinetic energy of blood flow is only about 1% of the total work output of the ventricle and therefore is ignored in the calculation of the total stroke work output. But in certain abnormal conditions, such as aortic stenosis, in which blood flows with great velocity through the stenosed valve, more than 50% of the total work output may be required to create kinetic energy of blood flow. Graphical analysis of ventricular pumping. Figure 9.8 shows a diagram that is especially useful in explaining the pumping mechanics of the left ventricle. The most important components of the diagram are the two curves labeled diastolic pressure and systolic pressure. These curves are volume pressure curves. The diastolic pressure curve is determined by filling the heart with progressively greater volumes of blood and then measuring the diastolic pressure immediately before ventricular contraction occurs, which is the end diastolic pressure of the ventricle. The systolic pressure curve is determined by recording the systolic pressure achieved during ventricular contraction at each volume of filling. Until the volume of the non-contracting ventricle rises above about 150 milliliters, the diastolic pressure does not increase greatly. Therefore, up to this volume, blood can flow easily into the ventricle from the atrium. Above 150 milliliters, the ventricular diastolic pressure increases rapidly, partly because of fibrous tissue in the heart that will stretch no more and partly because the pericardium that surrounds the heart becomes filled nearly to its limit. During ventricular contraction, the systolic pressure increases even at low ventricular volumes and reaches a maximum at a ventricular volume of 150 to 170 milliliters. Then, as the volume increases still further, the systolic pressure actually decreases under some conditions, as demonstrated by the falling systolic pressure curve in Figure 9.8. Because at these great volumes, the actin and myosin filaments of the cardiac muscle fibers are pulled apart far enough that the strength of each cardiac fiber contraction becomes less than optimal. Note especially in the figure that the maximum systolic pressure for the normal left ventricle is between 250 and 300 mm Hg, but this varies widely with each person's heart strength and degree of heart stimulation by cardiac nerves. For the normal right ventricle, the maximum systolic pressure is between 60 and 80 mm Hg. Volume pressure diagram during the cardiac cycle, cardiac work output. The red lines in Figure 9.8 form a loop called the volume pressure diagram of the cardiac cycle for normal function of the left ventricle. A more detailed version of this loop is shown in Figure 9.9. It is divided into 4 phases. Phase I, period of filling. This phase in the volume pressure diagram begins at a ventricular volume of about 50 milliliters and a diastolic pressure of 2 to 3 millimeters Hg. The amount of blood that remains in the ventricle after the previous heartbeat, 50 milliliters, is called the end systolic volume. As venous blood flows into the ventricle from the left atrium, the ventricular volume normally increases to about 120 milliliters, called the end diastolic volume, an increase of 70 milliliters. Therefore, the volume pressure diagram during phase I extends along the line labeled I, from point A to point B, with the volume increasing to 120 milliliters and there. Diastolic pressure rising to about 5 to 7 millimeters Hg. Phase II, period of isovolumic contraction. During isovolumic contraction, the volume of the ventricle does not change because all valves are closed. However, the pressure inside the ventricle increases to equal the pressure in the aorta, at a pressure value of about 80 millimeters Hg, as depicted by point C. Phase III, period of ejection. During ejection, the systolic pressure rises even higher because of still more contraction of the ventricle. At the same time, the volume of the ventricle decreases because the aortic valve has now opened and blood flows out of the ventricle into the aorta. Therefore, the curve labeled III, or period of ejection, traces the changes in volume and systolic pressure during this period of ejection. Phase IV, period of isovolumic relaxation. At the end of the period of ejection, point D, the aortic valve closes, and the ventricular pressure falls back to the diastolic pressure level. The line labeled IV traces this decrease in intraventricular pressure without any change in volume. Thus, the ventricle returns to its starting point, with about 50 milliliters of blood left in the ventricle and at an atrial pressure of 2 to 3 millimeters Hg. Readers well trained in the basic principles of physics will recognize that the area subtended by this functional period of ejection, period of filling figure 9-8 relationship between left ventricular volume and intraventricular pressure during diastole and systole. Also shown by the heavy red lines is the volume pressure diagram, demonstrating changes in intraventricular volume and pressure during the normal cardiac cycle. Net external work. Volume pressure diagram, the tan shaded area, labeled U, represents the net external work output of the ventricle during its contraction cycle. In experimental studies of cardiac contraction, this diagram is used for calculating cardiac work output. When the heart pumps large quantities of blood, the area of the work diagram becomes much larger. That is, it extends far to the right because the ventricle fills with more blood during diastole. It rises much higher because the ventricle contracts with greater pressure, and it usually extends further to the left because the ventricle contracts to a smaller volume, especially if the ventricle is stimulated to increased activity by the sympathetic nervous system. Concepts of preload and afterload. In assessing the contractile properties of muscle, it is important to specify the degree of tension on the muscle when it begins to contract, which is called the preload, and to specify the load against which the muscle exerts its contractile force, which is called the afterload. For cardiac contraction, the preload is usually considered to be the end diastolic pressure when the ventricle has become filled. The afterload of the ventricle is the pressure in the aorta leading from the ventricle. In figure 9-8, this corresponds to the systolic pressure described by the phase III curve of the volume pressure diagram. Sometimes the afterload is loosely considered to be the resistance in the circulation rather than the pressure. The importance of the concepts of preload and afterload is that in many abnormal functional states of the heart or circulation, the pressure during filling of the ventricle, the preload, the arterial pressure against which the ventricle must contract, the afterload, or both are severely altered from normal. Chemical energy required for cardiac contraction, oxygen utilization by the heart. Heart muscle, like skeletal muscle, uses chemical energy to provide the work of contraction. Approximately 70 to 90% of this energy is normally derived from oxidative metabolism of fatty acids, with about 10 to 30% coming from other nutrients, especially lactate and glucose. Therefore, the rate of oxygen consumption by the heart is an excellent measure of the chemical energy liberated while the heart performs its work. The different chemical reactions that liberate this energy are discussed in chapters 67 and 68. Experimental studies have shown that oxygen consumption of the heart and the chemical energy expended during contraction are directly related to the total shaded area in Figure 9.8. This shaded portion consists of the external work, U, as explained earlier, and an additional portion called the potential energy, labeled P. The potential energy represents additional work that could be accomplished by contraction of the ventricle if the ventricle should empty completely all the blood in its chamber with each contraction. Oxygen consumption has also been shown to be nearly proportional to the tension that occurs in the heart muscle during contraction multiplied by the duration of time that the contraction persists, called the tension time index. Because tension is high when systolic pressure is high, correspondingly more oxygen is used. Also, much more chemical energy is expended even at normal systolic pressures when the ventricle is abnormally dilated, because the heart muscle tension during contraction is proportional to pressure times the diameter of the ventricle. This becomes especially important in heart failure where the heart ventricle is dilated and, paradoxically, the amount of chemical energy required for a given amount of work output is greater than normal even though the heart is already failing. Figure 9.9. The volume pressure diagram demonstrating changes in intraventricular volume and pressure during a single cardiac cycle, red line. The tan shaded area represents the net external work, U, output by the left ventricle during the cardiac cycle. Efficiency of cardiac contraction. During heart muscle contraction, most of the expended chemical energy is converted into heat and a much smaller portion into work output. The ratio of work output to total chemical energy expenditure is called the efficiency of cardiac contraction, or simply efficiency of the heart. Maximum efficiency of the normal heart is between 20 and 25%. In heart failure, this can decrease to as low as 5 to 10%. Regulation of heart pumping. When a person is at rest, the heart pumps only 4 to 6 liters of blood each minute. During severe exercise, the heart may be required to pump 4 to 7 times this amount. The basic means by which the volume pumped by the heart is regulated are 1. Intrinsic cardiac regulation of pumping in response to changes in volume of blood flowing into the heart, and 2. Control of heart rate and strength of heart pumping by the autonomic nervous system. Intrinsic regulation of heart pumping. The Frank-Starling mechanism. In Chapter 20, we will learn that under most conditions, the amount of blood pumped by the heart each minute is normally determined almost entirely by the rate of blood flow into the heart from the veins, which is called venous return. That is, each peripheral tissue of the body controls its own local blood flow, and all the local tissue flows combine and return by way of the veins to the right atrium. The heart, in turn, automatically pumps this incoming blood into the artery so that it can flow around the circuit again. This intrinsic ability of the heart to adapt to increasing volumes of inflowing blood is called the Frank-Starling mechanism of the heart, in honor of Otto Frank and Ernest Starling, two great physiologists of a century ago. Basically, the Frank-Starling mechanism means that the greater the heart muscle is stretched during filling, the greater is the force of contraction and the greater the quantity of blood pumped into the aorta. Or, stated another way, within physiologic limits, the heart pumps all the blood that returns to it by the way of the veins. What is the explanation of the Frank-Starling mechanism? When an extra amount of blood flows into the ventricles, the cardiac muscle itself is stretched to greater length. This in turn causes the muscle to contract with increased force because the actin and myosin filaments are brought to a more nearly optimal degree of overlap for force generation. Therefore, the ventricle, because of its increased pumping, automatically pumps the extra blood into the arteries. This ability of stretched muscle, up to an optimal length, to contract with increased work output is characteristic of all striated muscle, as explained in Chapter 6, and is not simply a characteristic of cardiac muscle. In addition to the important effect of lengthening the heart muscle, still another factor increases heart pumping when its volume is increased. Stretch of the right atrial wall directly increases the heart rate by 10 to 20%. This, too, helps increase the amount of blood pumped each minute, although its contribution is much less than that of the Frank-Starling mechanism. Ventricular function curves. One of the best ways to express the functional ability of the ventricles to pump blood is by ventricular function curves, as shown in figures 9.10 and 9.11. Figure 9.10 shows a type of ventricular function curve called the stroke work output curve. Note that as the atrial pressure for each side of the heart increases, the stroke work output for that side increases until it reaches the limit of the ventricle's pumping ability. Figure 9.11 shows another type of ventricular function curve called the ventricular volume output curve. The two curves of this figure represent function of the two ventricles of the human heart based on data extrapolated from lower animals. As the right and left atrial pressures increase, the respective ventricular volume outputs per minute also increase. Figure 9.10. Left and right ventricular function curves recorded from dogs, depicting ventricular stroke work output as a function of left and right mean atrial pressures. Curves reconstructed from Figure 9.11. Approximate normal right and left ventricular volume output curves for the normal resting human heart is extrapolated from data obtained in dogs and data from human beings. Thus, ventricular function curves are another way of expressing the Frank-Starling mechanism of the heart. That is, as the ventricles fill in response to higher atrial pressures, each ventricular volume and strength of cardiac muscle contraction increase, causing the heart to pump increased quantities of blood into the arteries. Control of the heart by the sympathetic and parasympathetic nerves. The pumping effectiveness of the heart also is controlled by the sympathetic and parasympathetic, vagus, nerves, which abundantly supply the heart, as shown in figure 9.12. For given levels of atrial pressure, the amount of blood pumped each minute, cardiac output, often can be increased more than 100% by sympathetic stimulation. By contrast, the output can be decreased to as low as 0 or almost 0 by vagal, parasympathetic, stimulation. Mechanisms of excitation of the heart by the sympathetic nerves. Strong sympathetic stimulation can increase the heart rate in young adult humans from the normal rate of 70 beats per minute up to 180 to 200 and, rarely, even 250 beats per minute. Also, sympathetic stimulation increases the force of heart contraction to as much as double normal, thereby increasing the volume of blood pumped and increasing the ejection pressure. Thus, sympathetic stimulation often can increase the maximum cardiac output as much as twofold to threefold, in addition to the increased output caused by the Frank-Starling mechanism already discussed. Conversely, inhibition of the sympathetic nerves to the heart can decrease cardiac pumping to a moderate extent in the following way. Under normal conditions, the sympathetic nerve fibers to the heart discharge continuously at a slow rate that maintains pumping at about 30% above that with no sympathetic stimulation. Therefore, when the activity of the sympathetic nervous system is depressed below normal, this decreases both heart rate and strength of ventricular muscle contraction, thereby decreasing the level of cardiac pumping as much as 30% below normal. Parasympathetic, vagal, stimulation of the heart. Strong stimulation of the parasympathetic nerve fibers in the vagus nerves to the heart can stop the heartbeat for a few seconds, but then the heart usually escapes and beats at a rate of 20 to 40 beats per minute as long as the parasympathetic stimulation continues. In addition, strong vagal stimulation can decrease the strength of heart muscle contraction by 20 to 30%. The vagal fibers are distributed mainly to the atria and not much to the ventricles, where the power contraction of the heart occurs. This explains the effect of vagal stimulation mainly to decrease heart rate rather than to decrease greatly the strength of heart contraction. Nevertheless, the great decrease in heart rate combined with a slight decrease in heart contraction strength can decrease ventricular pumping 50% or more. Effect of sympathetic or parasympathetic stimulation on the cardiac function curve. Figure 9.13 shows 4 cardiac function curves. They are similar to the ventricular function curves of Figure 9.11. However, they represent function of the entire heart rather than of a single ventricle. They show the relation between right atrial pressure at the input of the right heart and cardiac output from the left ventricle into the aorta. The curves of Figure 9.13 demonstrate that at any given right atrial pressure, the cardiac output increases during increased sympathetic stimulation and decreases during increased parasympathetic stimulation. These changes in output caused by autonomic nervous system stimulation result both from changes in heart rate and from changes in contractile strength of the heart because both change in response to the nerve stimulation. Effect of potassium and calcium ions on heart function. In the discussion of membrane potentials in Chapter 5, it was pointed out that potassium ions have a marked effect on membrane potentials, and in Chapter 6 it was noted that calcium ions play an especially important role in activating the muscle contractile process. Therefore, it is to be expected that the concentration of each of these two ions in the extracellular fluids should also have important effects on cardiac pumping. Effect of potassium ions. Excess potassium in the extracellular fluids causes the heart to become dilated and flaccid and also slows the heart rate. Large quantities also can block conduction of the cardiac impulse from the atria to the ventricles through the AV bundle. Elevation of potassium concentration to only 8 to 12 mg/L, 2 to 3 times the normal value, can cause such weakness of the heart and abnormal rhythm that death occurs. These effects result partially from the fact that a high potassium concentration in the extracellular fluids decreases the resting membrane potential in the cardiac muscle fibers, as explained in Chapter 5. That is, high extracellular fluid potassium concentration partially depolarizes the cell membrane, causing the membrane potential to be less negative. As the membrane potential decreases, the intensity of the action potential also decreases, which makes contraction of the heart progressively weaker. Effect of calcium ions. An excess of calcium ions causes effects almost exactly opposite to those of potassium ions, causing the heart to go towards spastic contraction. This is caused by a direct effect of calcium ions to initiate the cardiac contractile process, as explained earlier in the chapter. Conversely, deficiency of calcium ions causes cardiac flaccidity, similar to the effect of high potassium. Fortunately, calcium ion levels in the blood normally are regulated within a very narrow range. Therefore, cardiac effects of abnormal calcium concentrations are seldom of clinical concern. Effect of temperature on heart function. Increased body temperature, as occurs when one has fever, causes a greatly increased heart rate, sometimes to double normal. Decreased temperature causes a greatly decreased heart rate, falling to as low as a few beats per minute when a person is near death from hypothermia in the body temperature range of 60 degrees to 70 degrees Fahrenheit. These effects presumably result from the fact that heat increases the permeability of the cardiac muscle membrane to ions that control heart rate, resulting in acceleration of their self-excitation process. Contractile strength of the heart often is enhanced temporarily by a moderate increase in temperature, as occurs during body exercise, but prolonged elevation of temperature exhausts the metabolic systems of the heart and eventually causes weakness. Therefore, optimal function of the heart depends greatly on proper control of body temperature by the temperature control mechanisms he explained in Chapter 73. Increasing the arterial pressure load, up to a limit, does not decrease the cardiac output. Note in Figure 9.14 that increasing the arterial pressure in the aorta does not decrease the cardiac output until the mean arterial pressure rises above about 160 mm Hg. In other words, during normal function of the heart at normal systolic arterial pressures, 80 to 140 mm Hg, the cardiac output is determined almost entirely by the ease of blood flow through the body's tissues, which in turn controls venous return of blood to the heart. This is the principal subject of Chapter 20. Chapter 10. Rhythmical excitation of the heart. The heart is endowed with a special system for 1. Generating rhythmical electrical impulses to cause rhythmical contraction of the heart muscle and 2. Conducting these impulses rapidly through the heart. When this system functions normally, the atria contract about 1/6 of a second ahead of ventricular contraction, which allows filling of the ventricles before they pump the blood through the lungs and peripheral circulation. Another special importance of the system is that it allows all portions of the ventricles to contract almost simultaneously, which is essential for most effective pressure generation in the ventricular chambers. This rhythmical and conductive system of the heart is susceptible to damage by heart disease, especially by ischemia of the heart tissues resulting from poor coronary blood flow. The effect is often a bizarre heart rhythm or abnormal sequence of contraction of the heart chambers, and the pumping effectiveness of the heart often is affected severely, even to the extent of causing death. Specialized excitatory and conductive system of the heart. Figure 10.1 shows the specialized excitatory and conductive system of the heart that controls cardiac contractions. The figure shows the sinus node, also called sinoatrial or SA node, in which the normal rhythmical impulses are generated, the internodal pathways that conduct impulses from the sinus node to the atrioventricular AV node, the AV node, in which impulses from the atria are delayed before passing into the ventricles, the AV bundle, which conducts impulses from the atria into the ventricles, and the left and right bundle branches of Purkinje fibers, which conduct the cardiac impulses to all parts of the ventricles. Sinus, sinoatrial, node. The sinus node, also called sinoatrial node, is a small, flattened, ellipsoid strip of specialized cardiac muscle about 3 mm wide, 15 mm long, and 1 mm thick. It is located in the superior posterolateral wall of the right atrium immediately below and slightly lateral to the opening of the superior vena cava. The fibers of this node have almost no contractile muscle filaments and are each only 3 to 5 micrometers in diameter, in contrast to a diameter of 10 to 15 micrometers for the surrounding atrial muscle fibers. However, the sinus nodal fibers connect directly with the atrial muscle fibers so that any action potential that begins in the sinus node spreads immediately into the atrial muscle wall. Automatic electrical rhythmicity of the sinus fibers. Some cardiac fibers have the capability of self-excitation, a process that can cause automatic rhythmical discharge and contraction. This is especially true of the fibers of the heart's specialized conducting system, including the fibers of the sinus node. For this reason, the sinus node ordinarily controls the rate of beat of the entire heart, as discussed in detail later in this chapter. First, let us describe this automatic rhythmicity. Mechanism of sinus nodal rhythmicity. Figure 10.2 shows action potentials recorded from inside a sinus nodal fiber for 3 heartbeats and, by comparison, a single ventricular muscle fiber action potential. Note that the resting membrane potential of the sinus nodal fiber between discharges has a negativity of about -55 to -60 mV, in comparison with -85 to -90 mV for the ventricular muscle fiber. The cause of this lesser negativity is that the cell membranes of the sinus fibers are naturally leaky to sodium and calcium ions, and positive charges of the entering sodium and calcium ions neutralize some of the intracellular negativity. Before attempting to explain the rhythmicity of the sinus nodal fibers, first recall from the discussions of chapters 5 and 9 that cardiac muscle has 3 types of membrane ion channels that play important roles in causing the voltage changes of the action potential. They are 1. Fast sodium channels, 2. Slow sodium-calcium channels, and 3. Potassium channels. Opening of the fast sodium channels for a few 10,000 ths of a second is responsible for the rapid upstroke spike of the action potential observed in ventricular muscle, because of rapid influx of positive sodium ions to their interior of the fiber. Then the plateau of the ventricular action potential is caused primarily by slower opening of the slow sodium-calcium channels, which lasts for about 0.3 seconds. Finally, opening of potassium channels allows diffusion of large amounts of positive potassium ions in the outward direction through the fiber membrane and returns the membrane potential to its resting level. But there is a difference in the function of these channels in the sinus nodal fiber because the resting potential is much less negative, only -55 mV in the nodal fiber instead of the -90 mV in the ventricular muscle fiber. At this level of -55 mV, the fast sodium channels mainly have already become inactivated, which means that they have become blocked. The cause of this is that any time the membrane potential remains less negative than about -55 mV for more than a few milliseconds, the inactivation gates on the inside of the cell membrane that close the fast sodium channels become closed and remain so. Therefore, only the slow sodium-calcium channels can open, that is, can become activated, and thereby cause the action potential. As a result, the atrial nodal action potential is slower to develop than the action potential of the ventricular muscle. Also, after the action potential does occur, return of the potential to its negative state occurs slowly as well, rather than the abrupt return that occurs for the ventricular fiber. Self-excitation of sinus nodal fibers. Because of the high sodium ion concentration in the extracellular fluid outside the nodal fiber, as well as a moderate number of already open sodium channels, positive sodium ions from outside the fibers normally tend to leak to the inside. Therefore, between heartbeats, influx of positively charged sodium ions causes a slow rise in the resting membrane potential in the positive direction. Thus, as shown in Figure 10.2, the resting potential gradually rises and becomes less negative between each 2 heartbeats. When the potential reaches a threshold voltage of about -40 mV, the sodium-calcium channels become activated, thus causing the action potential. Therefore, basically, the inherent leakiness of the sinus nodal fibers to sodium and calcium ions causes their self-excitation. Why does this leakiness to sodium and calcium ions not cause the sinus nodal fibers to remain depolarized all the time? The answer is that 2 events occur during the course of the action potential to prevent this. First, the sodium-calcium channels become inactivated, that is, they close, within about 100 to 150 milliseconds after opening, and second, at about the same time, greatly increased numbers of potassium channels open. Therefore, influx of positive calcium and sodium ions through the sodium-calcium channels ceases, while at the same time large quantities of positive potassium ions diffuse out of the fiber. Both of these effects reduce the intracellular potential back to its negative resting level and therefore terminate the action potential. Furthermore, the potassium channels remain open for another few tenths of a second, temporarily continuing movement of positive charges out of the cell, with resultant excess negativity inside the fiber. This is called hyperpolarization. The hyperpolarization state initially carries the resting membrane potential down to about -55 to -60 mV at the termination of the action potential. Why is this new state of hyperpolarization not maintained forever? The reason is that during the next few tenths of a second after the action potential is over, progressively more and more potassium channels close. The inward-leaking sodium and calcium ions once again overbalance the outward flux of potassium ions, and this causes the resting potential to drift upward once more, finally reaching the threshold level for discharge at a potential of about -40 mV. Then the entire process begins again, self-excitation to cause the action potential, recovery from the action potential, hyperpolarization after the action potential is over, drift of the resting potential to threshold, and finally re-excitation to elicit another cycle. This process continues indefinitely throughout a person's life. Internodal pathways and transmission of the cardiac impulse through the atria. The ends of the sinus nodal fibers connect directly with surrounding atrial muscle fibers. Therefore, action potentials originating in the sinus node travel outward into these atrial muscle fibers. In this way, the action potential spreads through the entire atrial muscle mass and, eventually, to the AV node. The velocity of conduction in most atrial muscle is about 0.3 meters per second, but conduction is more rapid, about 1 meter per second, in several small bands of atrial fibers. One of these, called the anterior interatrial band, passes through the anterior walls of the atria to the left atrium. In addition, 3 other small bands curve through the anterior, lateral, and posterior atrial walls and terminate in the AV node, shown in figures 10.1 and 10.3. These are called, respectively, the anterior, middle, and posterior internodal pathways. The cause of more rapid velocity of conduction in these bands is the presence of specialized conduction fibers. These fibers are similar to even more rapidly conducting Purkinje fibers of the ventricles, which are discussed as follows. Atrioventricular node and delay of impulse conduction from the atria to the ventricles. The atrial conductive system is organized so that the cardiac impulse does not travel from the atria into the ventricles too rapidly. This delay allows time for the atria to empty their blood into the ventricles before ventricular contraction begins. It is primarily the AV node and its adjacent conductive fibers that delay this transmission into the ventricles. The AV node is located in the posterior wall of the right atrium immediately behind the tricuspid valve, as shown in Figure 10.1. And Figure 10.3 shows diagrammatically the different parts of this node, plus its connections with the entering atrial internodal pathway fibers and the exiting AV bundle. The figure also shows the approximate intervals of time in fractions of a second between initial onset of the cardiac impulse in the sinus node and its subsequent appearance in the AV nodal system. Note that the impulse, after traveling through the internodal pathways, reaches the AV node about 0.03 second after its origin in the sinus node. Then there is a delay of another 0.09 second in the AV node itself before the impulse enters the penetrating portion of the AV bundle, where it passes into the ventricles. A final delay of another 0.04 second occurs mainly in this penetrating AV bundle, which is composed of multiple small fascicles passing through the fibrous tissue separating the atria from the ventricles. Thus, the total delay in the AV nodal and AV bundle system is about 0.13 second. This, in addition to the initial conduction delay of 0.03 second from the sinus node to the AV node, makes a total delay of 0.16 second before the excitatory signal finally reaches the contracting muscle of the ventricles. Cause of the slow conduction. The slow conduction in the transitional, nodal, and penetrating AV bundle fibers is caused mainly by diminished numbers of gap junctions between successive cells in the conducting pathways, so there is great resistance to conduction of excitatory ions from one conducting fiber to the next. Therefore, it is easy to see why each succeeding cell is slow to be excited. Rapid transmission in the ventricular Purkinje system. Special Purkinje fibers lead from the AV node through the AV bundle into the ventricles. Except for the initial portion of these fibers where they penetrate the AV fibrous barrier, they have functional characteristics that are quite the opposite of those of the AV nodal fibers. They are very large fibers, even larger than the normal ventricular muscle fibers, and they transmit action potentials at a velocity of 1.5 to 4.0 meters per second, a velocity about 6 times that in the usual ventricular muscle and 150 times that in some of the AV nodal fibers. This allows almost instantaneous transmission of the cardiac impulse throughout the entire remainder of the ventricular muscle. The rapid transmission of action potentials by Purkinje fibers is believed to be caused by a very high level of permeability of the gap junctions at the intercalated discs between the successive cells that make up the Purkinje fibers. Therefore, ions are transmitted easily from one cell to the next, thus enhancing the velocity of transmission. The Purkinje fibers also have very few myofibrils, which means that they contract little or not at all during the course of impulse transmission. One-way conduction through the AV bundle. A special characteristic of the AV bundle is the inability, except in abnormal states, of action potentials to travel backward from the ventricles to the atria. This prevents re-entry of cardiac impulses by this route from the ventricles to the atria, allowing only forward conduction from the atria to the ventricles. Furthermore, it should be recalled that everywhere, except at the AV bundle, the atrial muscle is separated from the ventricular muscle by a continuous fibrous barrier, a portion of which is shown in Figure 10.3. This barrier normally acts as an insulator to prevent passage of the cardiac impulse between atrial and ventricular muscle through any other route besides forward conduction through the AV bundle itself. In rare instances, an abnormal muscle bridge does penetrate the fibrous barrier elsewhere besides at the AV bundle. Under such conditions, the cardiac impulse can re-enter the atria from the ventricles and cause a serious cardiac arrhythmia. Distribution of the Purkinje fibers in the ventricles, the left and right bundle branches. After penetrating the fibrous tissue between the atrial and ventricular muscle, the distal portion of the AV bundle passes downward in the ventricular septum for 5 to 15 mm toward the apex of the heart, as shown in Figures 10.1 and 10.3. Then the bundle divides into left and right bundle branches that lie beneath the endocardium on the two respective sides of the ventricular septum. Each branch spreads downward toward the apex of the ventricle, progressively dividing into smaller branches. These branches in turn course sidewise around each ventricular chamber and back toward the base of the heart. The ends of the Purkinje fibers penetrate about 1/3 of the way into the muscle mass and finally become continuous with the cardiac muscle fibers. From the time the cardiac impulse enters the bundle branches in the ventricular septum until it reaches the terminations of the Purkinje fibers, the total elapsed time averages only 0.03 seconds. Therefore, once the cardiac impulse enters the ventricular Purkinje conductive system, it spreads almost immediately to the entire ventricular muscle mass. Transmission of the cardiac impulse in the ventricular muscle. Once the impulse reaches the ends of the Purkinje fibers, it is transmitted through the ventricular muscle mass by the ventricular muscle fibers themselves. The velocity of transmission is now only 0.3 to 0.5 meters per second, 1/6 that in the Purkinje fibers. The cardiac muscle wraps around the heart in a double spiral, with fibrous septa between the spiraling layers. Therefore, the cardiac impulse does not necessarily travel directly outward toward the surface of the heart but instead angulates toward the surface along the directions of the spirals. Because of this, transmission from the endocardial surface to the epicardial surface of the ventricle requires as much as another 0.03 second, approximately equal to the time required for transmission through the entire ventricular portion of the Purkinje system. Thus, the total time for transmission of the cardiac impulse from the initial bundle branches to the last of the ventricular muscle fibers in the normal heart is about 0.06 second. Summary of the spread of the cardiac impulse. Through the heart, Figure 10.4 shows in summary form the transmission of the cardiac impulse through the human heart. The numbers on the figure represent the intervals of time, in fractions of a second, that lapse between the origin of the cardiac impulse in the sinus node and its appearance at each respective point in the heart. Note that the impulse spreads